let's see. Okay, for some reason the microphone is giving me some headaches, so I said I'm just going to bring this. So if you're wondering why I have like a podcast microphone there in the room, that's why. Because I didn't want the lecture recording to cancel again. So, okay, let's get started. I think here I do it again. That's 5. That's what happens when I copy and paste. Okay, so how did the Excel homework go? Pretty straightforward, hopefully? Okay, good. I want to make sure that everybody's clear on one thing regarding the homework schedule. So there's going to be a homework due next Monday, the 9th. There's a homework due the 11th, but there is not a homework due on the 13th because your first submission of your project's due. So I made it a point to not have a homework and a project submission on the same day. Sound good? Okay. A couple things, and I just wanted to make sure everybody's clear on the project because I've had a couple questions about this. You do not need to analyze the trusses, and you do not need to pick members. Okay, I'm not like when I say pick members, you don't need to pick W12s or anything like that. Okay, all I'm after are the truss layouts. Make sure that they're laid out based on project constraints. Make sure that IT is 0. Make sure that the member lengths are fine, that they fit within the envelope. And then I want you to choose one for final design and describe your selection strategy. That's it, okay? The reason I don't want you to analyze the truss is because you're not going to have to analyze the truss by hand because I'm going to show you a software package called Mascan that'll do it for you, okay? That's part of the purpose of the project is to get you to use Mascan on your own for your truss, okay? So there is no need to analyze the truss. So, I don't think that submission 1 is going to be much more work than a typical homework assignment, okay? I don't think it's not meant to be a ton of effort, okay? The work will come, so the way that we'll do the project, just so you're aware, the work will come primarily in submission 2. And so the week before Thanksgiving break, we'll have a lecture on Monday. Wednesday will be sort of like a Q&A session, so I won't really come in on Wednesday with lecture notes. That Wednesday I'll come in and we'll just be troubleshooting your projects. If you want to come in and do some work on your project, that's what I'm here to do. The project will be due the Friday of Thanksgiving week, but I'm not going to have class that Friday. So if you turn it in early, you don't have to worry about this class till after Turkey. Is that okay? Unless you want to meet the Friday of Thanksgiving break, or right before Thanksgiving break. Oh, you do? Okay, well, I'll come up with a lecture. It's the rain, is that what it is? Just the rain and that it's Friday and that you're engineers, the F stands for fun. The H stands for happiness. That was a joke, not a very funny one. Okay, all right. Let's get into the wonderful world of concentrated moments, okay? What we're going to do today is we're going to continue our discussion of shear and moment diagrams. I don't have much left in the way of things that you haven't dealt with before. We have done triangular loads, we've done distributed loads, we've done concentrated loads, we've done simple supports. There's really only a couple things left. We have hinges, which we're going to do on Monday. We have frames, which really the only difference between a shear and moment diagram for a beam and a frame is instead of drawing them like this, you're drawing them like that. It's not really any different. But we haven't dealt with concentrated moments. And concentrated moments will present a unique challenge, if you will. And I want to show you how that works. Now, to be clear, nothing changes from a theoretical perspective. We're still using the same relationship between load and shear and the same relationship between shear and moment. But we're going to find some things that are a little different, and I don't want to go too far down the rabbit hole, but you'll kind of see what I mean when we start checking things out. So it's still the same relationship here and here, but maybe a little bit of an addendum to the relationship between shear and moment, but it's easier to do that when you see it. What happens with concentrated moments is that so if we look at between loads, the load is 0, but a concentrated moment is not a shear. It's not a vertical force. So a concentrated moment will have zero impact on your shear diagram. In fact, when you're drawing your shear diagram, you can sort of ignore the concentrated moment. It doesn't exist. Okay. What we're going to find is that the areas are not going to match up. And what I mean by that is when you sum your areas for your shear diagram, they're not going to be zero. Okay. But you'll see why. And once you see the math and you see the numbers, you'll go, oh, okay, this isn't so bad. Concentrated moments and how we deal with concentrated moments is also going to affect the construction of shear and moment diagrams for cantilevered beams. So we're going to do two examples today, one with just a beam with a concentrated moment on it, and one with a cantilevered beam. So let's just get right into it. I've got two examples today, and I want to take our time with them. Now, because we've got two examples, I went ahead and gave you the reactions for them. But by the way, with this example 4, so this is going to be our first example, we already computed the reactions for it. We did the reactions for this problem a little while ago when we drew, when we handled reactions with concentrated moments. So we already computed in a previous example that AY was 15.2 kips and BY was 24.8 kips. So this problem we've already done. Okay. So what we're going to do is we're going to draw the shear and moment diagram for this beam. And again, like I said, we're going to see something kind of interesting with this. So I'm going to give everybody a minute or so to jot this down, and then we'll get into it. So let me make this maybe a little bit bigger. Give myself some room. While you all are doing that, what I'm going to do is I'm going to maybe scroll down like that so where you can just see the beam. And then I'm going to draw my little guidelines. Oh, I need to turn my little that on. Always forget to do that. So there's that. And again, I'm just drawing lines wherever there's a point of interest. You can't really draw too many of them, I don't think. I guess you could, but whatever helps you as the analyst. Okay. And then, let's see, we'll do, I like that. All right. So hopefully we start at 0 and end at 0. We'll see if we do. Let's see, is everybody good to go, or do you need a minute? Okay, I'll assume everybody's good to go. Okay, so I'm at 0. I'm going to need your help on this. So tell me what to do. So I'm at 0. What's the first thing that I do? There we go. So we go up 15.2. Okay, so go up 15.2. Now, from here to here, how far down do I go? Was that? 30, because it's 3 kips per foot over a distance of 10 feet. So if I'm at 15.2 and I drop down 30, what's that put me at? Negative 14.8. So, and how do I drop? What's the pattern? That's a linear diagonal pattern. About like that. And just so we're on the same page, what is the slope of that line? 3. Or if you wanted to be technical, negative 3. But the slope of that line comes from the load. Okay? That's where that comes from. Okay? Now from here to here, what happens? Straight across. No load, so constant load or constant shear with a 0 slope. Negative 14.8. So if I'm at negative 14.8 and I jump up 24.8, what's that put me at? Positive 10. Okay? So again, nothing. And then I come here. What do I do here? Nothing. It's not a shear, it's a moment. So I just ignore it. And I just keep on chugging. And then I get here, and that's 10, and I drop down. So if you want, you can put like a 10 right here if you'd like. But the point is that nothing happens there. This is not a moment, or this is not a shear, that's a moment. So I ignore that concentrated moment. I just ignore it, okay? Now, ignoring it is going to have a consequence, but you'll see what that is here in a bit. So far, so good? Okay. Now, we need to start determining areas, okay? So I'm going to start at the right, work my way left. So if I break this up, let's break this up. What's the area of this rectangle? It's 10 high and 10 foot wide. So this is 100, and that makes this one 102. And I'm going to put a positive on here. Okay. This rectangle right here is 14.8 times 15. What is that? 222. All right, and we'll call that negative. Okay. Now we got two triangles. How do we do that? Well, we need these bases. We need this distance and this distance. So let's label these. Let's call this x1. And x2. Can y'all see that in the back? Okay. So how do we compute x1? 15.2 kips divided by, what'd you say? 3. 3 kips per foot. Okay, 15.2 over 3. Might not be able to do that one in my head, but it's 5 something. Yeah, like that, something like that. And then x2 is going to be 14.8 kips over 3. And what is that? That's a little less. Isn't that something like 4 point, like that? Did I do that right? So help me out, all right? What's that area? This area. Let's do this one first. So it's 1/2, don't forget it's a triangle, 1/2 base, so x1 of this, so 1/2 5.067 times 15.2. And just do it to like 2 decimal places. That's enough. 38.51. All right, so positive 38.51. All right, what about that one? $36.5. It's probably 5.1 with the rounding, but 5.051 doesn't really matter. So you'll see why. Is everybody with me so far? Okay, now I want to show you something. All right? So I want everybody to watch this. Watch this up here. Okay, so let's do a little note over here to the side. Let's sum the areas. Okay, so let me write them in order. So what do we got? We got 38.51, negative 36.51, negative 222, positive 100, positive 100. What do we get? Interesting. Negative 20. What have we been getting this whole time? 0. We didn't get 0. We got negative 20. Interesting. Why do you think we got negative 20? Where does the 20 come from?
The concentrated moment.
The concentrated moment. The amount that the areas are imbalanced comes from that concentrated moment. That's what happened. Okay? Does that make sense? So let me show you how the moment diagram is going to work. Okay? All right, so do about like that. All right, and another thing, I'm going to draw another little guideline right there. And the reason I'm drawing it right there is because that's where the shear was 0. Like, why would I be interested in that? Because where the shear is 0, the moment is either maximized or minimized. So I just want to have that point indicated. Okay, so we're going to have a moment diagram in foot kips. Okay. We're going to start at 0. Okay. So tell me what's going to happen from here to here. How much am I going to increase from here to here? 38.51. Okay, so here it's going to be 38.51. All right. Is it going to be linear? It's going to be what? Quadratic. So it's going to be option 1 or option 2. Which way is it? Is it option 1 or option 2? 1, right? Because we have a positive slope here all the way to 0 slope. Okay? Now what happens from here to here? I'm at 38.51. What do I end up at? What's going to be the point right here? 2. It's really tiny. It's 2. Okay. And is it going to be quadratic as well? All right. Option 1, option 2. What's it going to be? 2. In fact, really what's going on is this is the same parabola. That's all the same parabola. I'm just drawing it in segments because I wanted to indicate the maximum. But that's all one parabola. Okay. Now I'm at 2. What do I do? I drop down. How much? So if I'm at 2, how much am I going to drop down from 2? So 2, I'm dropping down this much. So what's that going to put me at? 220, or negative 220, right? And what is the fashion in which I drop? What's that? It's linear, right? It's a straight line. And remind me, what is the slope of that line? Negative 14.8. Let me move this 220. I'm going to move this over here. Okay. Okay. Now I'm at negative 220. Let's go from here to here first. Let's go from here to here. So if I'm at negative 220, I'm going to increase 100, and I'm going to increase to negative 120, right? I can do a little better than that. Let's put that about right there. And don't forget the slope of that line is positive 10. Okay. Now, let's sort of like look into the future a little bit. If all I was doing was looking at the shear diagram, I were to increase another 100, and that's going to put me at negative 20. It's not going to close, right? So something needs to happen here. And what happens here? Well, by golly gosh gee, we have our concentrated moment. Okay? Now, what does our concentrated moment do to the moment diagram? Well, here's the way I look at it. The sum of the areas are negative 20, right? I need them to be 0. So this moment needs to be a sudden positive 20. It needs to go up, right? So I propose that right at this point, we have a sudden jump up to negative 100. And now we can increase to 0. And again, that line, positive 10. And that's all concentrated moments do. They're just, it's like a point load for moment diagrams. That's all it is. Okay. Let me stop for a sec. I want to see if you all have any questions on this. Sound good? It's not very difficult, is it? Hopefully it's not. Hopefully this is pretty straightforward. If you're okay with that, anybody need any more time on this? Okay, let's go on to the next one. Let's go on to our cantilevered beam. Okay, so Dr. Yoon would appreciate me because I tend to recycle. I'm using this problem from a previous example before. We computed the reactions on this one before, right? So I'm going to draw the shear and moment diagrams for this beam, and we've already computed reactions for it. This is a cantilevered beam, okay? Now, I have a cantilevered beam with an inclined load. Ooh, we haven't had an inclined load that we need to pay attention to what we do there. I'll show you about that here in a bit. We have a concentrated load of 20 kips at the end, and I have a moment reaction, a horizontal reaction, and a vertical reaction. I'm curious, how much impact is that horizontal reaction going to have on shear and moment diagrams? Not a bit. This is a shear diagram, moment diagram. It's not an axial force diagram. Like when we solve trusses and we put, like, here's the truss and this member is 28 kips in tension, this one's 40 kips in compression, what have you, that's an axial force diagram. That 6 kips doesn't matter at all, okay? And there's something telling there because that'll tell us what we do with this, okay? Everybody good? Okay, so let's go through the process like we had before. So, forgot it again. Gotta turn my little pen on. So, start at 0, and I'm not doing anything different, okay? I want to be clear that whenever we're constructing the shear diagram and the moment diagram for a cantilever beam, it's not like it's a different problem just because it's a different support system. The process is the same, nothing changes. So we're going to start at 0, and again, we're just going to do what the beam tells us to do. I'm looking at the beam, and it says, right there today, it says, Greg, go up 28 kips. So, okay, I'm going to listen to it. I'm going to go up 28 kips. Okay? So I'm going to say here, I'm going to go up 28, and I'm going to go right here. Okay? So I see nothing here. Now what do I do? Interesting. You didn't say down 10. You said down 8. By the way, you are correct. And why did you say down 8?
Because that is the
100% right. The shear diagram is about a change in vertical forces, not about a change in incline forces, right? So we need to determine the vertical component of this load. And the vertical component is 8 kips. See, the horizontal component is 6 kips. And if we're ignoring this, then we need to ignore that too, right? So that's why we're only considering the vertical component. So we drop down 8 to 20. Go over drop down to 0. Does that make sense? Okay. Now, what is the area of these components? What's the area of the first rectangle? 280. What's the area of this one? 200. Do these areas sum up to 0? Not even close, right? Not even close. What do they sum to? They sum up to 480. Anybody see a 480 somewhere on this shear diagram? Boom. The reaction, right? So what does that 480 do? What do I do with it? If I start at A, like, does that 480 cause a sudden jump upwards or a sudden jump downwards? Downwards, right? Because this is all positive area. I need a negative 480 so that I can use these positive areas to get me back up to 0, right? Okay, so oh, I'm doing the wrong thing. All right, so we start at 0, and then a sudden drop downward. And then we're going to go from 480 to negative 200, and then that back to 0. And so what we're going to have are two lines with slightly different slopes. And what are the slopes of those lines? Well, positive 28, positive 20. Does anybody have any questions on this? All right, I do want to mention a little bit about what we're going to do in the next lecture, but I won't be long, and you will probably get a little bit more time of your life back today, if that's okay. Okay. Do I need to lead this up, or are you all good? Y'all good? Okay. All right. Okay, I'm going to mention a couple of things, and I just want to highlight this. When we come back on Monday, we're going to have an example that's a little long, and so I kind of want to introduce it. I don't want to be rushing through it, but I haven't talked about this yet, internal indeterminacy, right? Remember how we did external indeterminacy, and then we did internal indeterminacy for trusses? We haven't done internal indeterminacy for beams and frames, okay? So I kind of want to just briefly mention that and then talk about a classic problem that we're going to have, which is shear and moment diagrams for beams with hinges, okay? So I'll skip through all this because I know we all know this. So remember that so far we've had two different issues with stability and determinacy. So we've had external indeterminacy, and we've had internal indeterminacy for trusses. So external indeterminacy we computed as R minus EC plus 3. So we took the total number of unknowns, which is the reactions, minus the total number of knowns, which is EC plus 3, because we have three equations of equilibrium. And that's how we determined external indeterminacy. Remember, the reactions can't all be concurrent, they can't all be parallel. For trusses, we had M plus R minus 2J. M plus R was the number of unknowns, all the reactions, and then one per member. And then the number of knowns, we had two equations of equilibrium for every joint, right? So unknowns minus knowns gave us our IT value. And remember, the truss has to be externally stable and has to be constrained against rigid body movements. And all that was saying is make sure you have triangles everywhere, okay? What we haven't discussed is internal indeterminacy for beams and frames. So I'll start off with frames. Whenever you have a frame, you have a little bit more unknowns and a little bit more knowns. So for your unknowns, what you have is you have your reactions, but for every member in the frame, remember how we had, like for trusses, we had M plus R because we had one unknown for every truss member? Well, for frames, we have three unknowns for every frame member, because for every frame member, we can have an axial force, we can have a shear, we can have a moment, right? So the unknowns in beams and frames is 3m plus r for the reactions and 3 unknowns for every member. The number of knowns is any equations of condition, but for every joint, we have 3 equations of equilibrium, not 2, because in a frame, we have potential moments. Does that make sense? So the internal indeterminacy for a beam and or for a frame is just 3m plus r minus 3j plus ec. Okay. One thing that's kind of interesting is, so what about beams? Well, a beam is just a frame with 2 joints and 1 member, right? I mean, there's a joint on each end and there's 1 member. So if you take this and you make m equals 1 and you make j equals 2, so you do all the math, you get this. So the internal indeterminacy for a beam is the same as IE. And I mean, I could show you, it's really not that difficult. So you have 3m plus r, and you have minus 3j plus EC. So if we're looking at any beam, right, there's 2 joints and 1 member, right? So this is 3 plus r minus 6 plus EC, you know, so 3 plus r minus 6 minus EC, so r minus 3 minus EC, or r minus 3 plus EC. So that's how we got that. So it's not like it's anything that's all that, you know, challenging. Does that make sense? So again, that's sort of a footnote. I'm not making a super big deal about it, but it's just plug and chug. The main reason that I show you this right here is because when you take your FE exam, if memory serves, the reference manual actually only lists 2 formulas. It lists this one and it lists this one. But the idea is if you're looking at external indeterminacy, you could just take m equals 1 and j equals 2 and get the same formula. So, make sense? Okay. Now, what I really want to discuss, at least to plant the seed, is I want to talk about internal hinges. This is a common misconception when students are doing this on homework problems, and particularly on exams. So I want to make a very fundamental point. One question we haven't answered is, how does an internal hinge affect how you construct a shear and moment diagram? The answer, it doesn't. Okay? Here's what I mean. Here's the longer answer. So whenever you have a beam that has an internal hinge, like this one, okay, so this is going to be the example that we do on Monday. So this beam has an internal hinge. What we're going to do is we're going to use that internal hinge, and we're going to use it to figure out the reaction here and the reactions here, right? After that, you can kind of ignore that hinge is even there, okay? Because I propose that whatever those reactions end up being, the values of those reactions satisfy both the equations of equilibrium for the entire structure and the equation of condition at the hinge. So that's what those reactions are doing. They're meeting the requirements of that hinge. So we still construct the shear diagram and construct the moment diagram normally. What ends up happening when we draw the moment diagram, what are we going to get on the moment diagram right here? 0. Because the internal moments in the beam at the hinge are 0. Okay? So what do? You use the hinge to compute the reactions, and then you just ignore it and draw the shear and moment diagrams normally. And if you do it correctly, you will get a 0 moment right there. Okay? That is how you construct the shear and moment diagram for a beam with an internal hinge. And to demonstrate that, we will do that on Monday. Okay? I said I would give you some time back, and I'm going to give you 15 minutes back. I'm going to pull up the code one more time in case you didn't get it. And I will see you all on Monday. Try and stay dry and have a wonderful weekend.